Hello guys, in this video we are going to know about the IR and OCV testing machine. So before we go into practical explanation, physically we have to know about machine. So this equipment is essential for assessing the insulation resistance and open circuit voltage, ensuring the reliability and safety of electrical components. Understanding how this machine operates and interpreting its results are crucial steps in maintaining high-quality standards in our processes. Let's dive into the details and see how this testing machine plays a vital role in our work. Let's talk about the key aspect of IR and OCV testing. First, this testing acts as a critical quality gate. The machine performs a mandatory inspection during battery pack manufacturing, ensuring that only qualified cells proceed to the assembly line. This step is vital for maintaining overall product quality and safety. Next, the testing process is incredibly rapid. It completes two essential electrical checks in just 100 milliseconds. This high-speed measurement helps keep the production line running efficiently without compromising accuracy. Finally, the technical side involves using a 1 kHz AC signal. This allows the system to accurately assess the electrical characteristics and internal condition of each battery cell, giving us valuable insights into its health and performance. Together, these features make IR and OCV testing a crucial part of quality control in battery manufacturing. Here, we're focusing on two key parameters that help us understand the health and status of battery cell. First, there's the open circuit voltage, or OCV. This measures the electrical potential of the cell when no load is connected. Essentially, it gives us a clear snapshot of the cell's current state of charge. It's important because a low OCV usually means the cell is either discharged or has undergone chemical degradation, which can affect its performance. Next, we have internal resistance, or IR. This tells us about the internal physical condition and the electrochemical health of the cell. It's measured in milliohms using AC impedance. A high internal resistance is a red flag. It often indicates that the cell is aged, damaged, or may have manufacturing defects. Monitoring both of these parameters is crucial for maintaining battery reliability and efficiency. Let's take a closer look at the measurement ranges and limits that are crucial for our testing process. Starting with internal resistance, or IR, we have two measurement modes, low gear and high gear. In low gear, the range is from 0.1 milliohms up to 200 milliohms, with a resolution of 0.1 milliohms, allowing for very precise readings of small resistance values. Switching to high gear, the range expands from 1 milliohm to 2 ohms, with a resolution of 1 milliohm. This broader range is useful when dealing with higher resistance values, but still maintains decent precision. When it comes to open circuit voltage, or OCV, the measurement range is from 0 to just under 20 volts, specifically 19.99 volts. The voltage resolution is 0.01 volts, enabling us to detect very subtle changes in voltage. It's critical to understand the hard limits imposed on these measurements. First, the cell voltage must never exceed 19.99 volts. Going beyond this limit isn't just a measurement error. It risks causing permanent damage to the machine. Second, the internal resistance of the cell must not surpass 2 ohms. If the resistance exceeds this threshold, the device won't display the actual value. Instead, it shows 99.99, indicating the cell is rejected due to an excessive resistance reading. Keeping these measurement ranges and limits in mind ensures both the accuracy of our testing and the safety of our equipment. Before we begin any testing, there are a few important preparation steps to ensure accurate results. First, we need to power on the machine and let it warm up for about 5 minutes. This allows the internal components to stabilize, which is crucial for getting reliable readings. Next, we perform an idle system check with no cell connected. Check the IR display. It should show a value between 0.0 and 0.9. If the readings are higher than this, take a moment to inspect the probe contacts and clean them if needed before moving on. Finally, we need to verify the environmental conditions. Make sure the operating temperature is within 0 to 50 degrees Celsius, as this range helps the sensors perform optimally during the test. Following these steps carefully helps ensure the accuracy and consistency of our test results. Now, let's go over how to set alarm limits step by step. First, you start by holding down the alarm setting key for 1 second to enter the alarm setup mode. Next, you select the alarm mode. You have 4 options here: 0, 1, 2, or 3. After choosing the mode, you adjust the alarm limits using 2 types of keys. The +10 and -10 keys allow you to make course adjustments quickly, while the +1 and -1 keys let you fine-tune the settings with precision. Once you've set the desired limits, press the Set button to save your changes and move on to the next limit. The limits follow the sequence: IR upper, IR lower, OCV upper, and then OCV lower. Now, let me explain each alarm mode to help you choose the right one. Mode 0 turns off the alarm completely, which is useful when you just want to take manual readings without interruptions. Mode 1 causes a device to beep when measurements fall within the set limits. This mode is great for mass production environments where quick confirmation is needed. Mode 2 is a standard mode, where the alarm beeps if values fall outside the limits, alerting you to potential issues. Finally, Mode 3 provides beeping feedback for both pass and fail conditions, offering full confirmation if you want detailed alerts. Understanding these modes and the setting sequence ensures you can tailor the alarms to fit your specific workflow and quality control needs. Let's walk through the step-by-step testing procedure. First, start with cell placement by aligning the cell center directly with the needle. Make sure to contact the negative terminal at the bottom first, then press down gently. Next, secure engagement by lowering the positive terminal onto the thimble. If needed, use a sliding plate to adjust for different cell lengths to ensure a snug fit. Once everything is in place, read the display. Wait about 100 milliseconds for the values to show up. The IR value will appear on the left and the OCV value will be on the right. When removing the cell, press down on the negative end, compress it before lifting away. Avoid pulling the cell out directly, as this can damage the pins. A quick pro tip: always make sure there is full contact between terminals. Loose contact is the #1 reason for incorrect IR readings, so proper alignment of the cell in the testing holder is really crucial. When evaluating cell quality, we look at 3 key factors: cell condition, IR reading, and OCV reading. For a new, healthy cell, the IR reading should be low and the OCV reading normal, which means the cell passes inspection and is good to go. An aged cell typically shows rising IR readings, while the OCV may still be normal. In this case, the cell requires monitoring but is not necessarily rejected immediately. Damaged or defective cells usually have high IR readings and variable OCV readings, leading to failure and removal from production. Deeply discharged cells show low IR and OCV readings and also fail, while overcharged cells may have normal IR but high OCV, which results in failure as well. The golden rule here is crucial. A cell must pass both IR and OCV limits to be accepted. Even if it fails one test, it gets removed from the batch to ensure the quality and reliability of the final product. Here, we're looking at the impact of cell matching on the battery pack assembly process. In automated assembly lines, it's crucial to use cells that are carefully matched to each other, especially when it comes to their internal resistance or IR. When cells have mismatched IR values, we run into what's called an imbalance problem. This means some cells charge faster than others during the charging cycle, which can cause instability in the entire system. This imbalance isn't just a minor inconvenience. It leads to several serious issues. First, there's a risk of overheating, which can compromise both safety and performance. Then, the overall capacity of the battery pack is reduced because some cells can't operate optimally. Over time, this mismatch shortens the battery's life, meaning your pack will need replacement sooner than expected. And perhaps most critically, these imbalances can create significant safety hazards. To prevent all these problems, testing for internal resistance and open circuit voltage, or OCV, is essential. These tests help ensure that each cell in the pack is electrically matched, which protects the pack performance, reliability, and most importantly, safety. Here's a quick reference guide for troubleshooting common issues you might encounter. First, if there's no display on startup, it's often because the power is either not switched on or the cable is loose. So, always start by checking that the switch is turned on and the cable is securely plugged in. If you see the IR display but no open circuit voltage, this usually means the cell polarity is reversed or a wire is disconnected. In this case, double check the connections and make sure the polarity is correct. When the display shows 99.99, it indicates the value has exceeded the rated range. The best course of action here is to reject the cell and verify that the gear selection is appropriate for the measurement. If the reading fluctuates, this often results from poor probe contact or dirty pins. To fix this, inspect the test pin tips and try reseating the cell to ensure a solid connection. Finally, if the reading is stuck or frozen, it might be because the pins are touching each other or a terminal is loose. Carefully separate any pins that are touching and check all terminal connections for tightness. These steps should help you quickly resolve most common problems. Safety is our top priority when working with testing equipment. First, always perform a visual inspection before powering on the machine. Check the instrument casing and insulation carefully for any signs of damage to prevent electrical hazards. Next, pay close attention to pin maintenance. If any test pin is damaged or disconnected, it must be replaced immediately. Never attempt a test with faulty pins, as this could lead to inaccurate results or even equipment damage. Finally, handle the equipment correctly by following the removal procedures exactly as instructed. This helps avoid mechanical stress on the testing interface, ensuring the longevity and reliability of your tools. Keeping these safety protocols in mind will help protect both you and the equipment during every test.